Hello and welcome to Kashmatics. In this tutorial, I'll show you how to solve first-order differential equations using a method called separating the variables. I'll explain how to find the general solution as well as the particular solution. Now you're going to need to be confident with logs, exponentials, partial fractions, reverse chain rule, integrating trig functions, and integration by parts. And I've got tutorials on most of those topics, so please go and watch those if you're feeling a bit rusty and need a recap. So grab yourselves a pen and some paper and let's get cracking. Now, before I go through any examples on separating the variables, I'm going to do a question of the type you would have done in year 1. Okay, so we've got dy by dx equals 4x minus 7. And we're told that when x equals 5, y equals 1. And what I'm going to try and do is write down y in terms of x. So we've got dy by dx equals 4x minus 7. Now, if I want to work out what y is, I just need to integrate this. So dy by dx becomes y, and this becomes the integral of 4x minus 7 dx. So y would equal 4x squared over 2, which is 2x squared, minus 7x plus c. Now this here is the general solution to this over here. Okay, so when I integrate this, this is the general solution. But if I want a particular solution, I need what are called boundary conditions, and that's what these are. Because if you've got a curve, y equals 2x minus 7x plus c could be a curve there, or it could be a curve there, or a curve there, or down here. We don't know exactly where it is, but once we're given some boundary conditions, we can work out exactly where that curve is. So let's just substitute these values in. So y equals 1, and this would be 2x squared, so 2 times 5 squared, take away 7 times 5 plus c. So 1 equals 2 times 25, which is 50, take away 35 plus c. So 1 is equal to 15 plus c, which gives me c equals minus 14. So my particular solution is y equals 2x squared minus 7x minus 14. So hopefully that's recapped something you'll have done in year 1. So let's move on to some examples where we're actually separating the variables. In year 2, the type of differential equations we look at are ones that can be solved by separating the variables. Now this is a method which can only be applied when the differential equation can be rearranged in the form f of y dy equals g of x dx. Okay, so everything with y on one side, everything with x on the other side. And the dy and the dx must be in the numerators. So I can't have f of y over dy or g of x over dx. Okay, so the first thing you do is rearrange the differential equation to get it in the form that I've got above. Okay, and what you do then is integrate each side respectively. And if you've got any boundary conditions, you substitute those to find the constant. And then what you do is write the Cartesian equation relating y and x in whatever form that's required from the question. Let's have a look at this example I've got on the right. I've got 1 plus x squared dy by dx equals x tan y. Now let's do the first step. We need to separate the variables, so everything with y on one side, everything with x on the other. And if I do that, I'll get 1 over tan y dy equals x over 1 plus x squared dx. Okay, and I can put my integration signs to say that's what I'm going to do with them. Now the right hand side is fine as it is, okay, and I need to recognize that that is the derivative over the function, so I need to use a natural log to integrate that. The right hand side is also derivative of a function because this is cos y over sine y dy. So for both of these sides I've got the reverse chain rule going on. Okay, it's derivative over function. So this becomes ln sine y, and this becomes ln 1 plus x squared, but I need to make sure I divide by 2 because when I multiply by the derivative of 1 plus x squared I get 2x, and I've only got an x here, so I need to divide by 2 to get rid of that extra 2. Plus, and the way I'm going to write this is ln c, because writing it as an ln is still a constant, I can actually combine these logs. So what I've got is ln sine y is equal to, now this term here is the equivalent of a half ln 1 plus x squared, so that's actually equal to ln of the square root of 1 plus x squared, add ln c, so I've got ln sine y equals ln, now I can bring the c over here, so c square root of 1 plus x squared, because when you add logs you can combine them by multiplying the terms. And what that means is sine y is equal to c square root of 1 plus x squared. And that is my general solution for this differential equation. Now in this question here, I'm after the particular solution, and the reason why I can do that is because I've got the boundary conditions. I know what x is and I know what corresponding value of y is. So what I can do is I can write down y as a function of x as a particular solution. So let's just go ahead and separate the variables first. I'm going to keep this 3 where it is. I'm going to move the y minus 2 onto this side and the dx onto the other side. So I get 1 over y minus 2 dy equals minus 3 over 2x plus 1 x plus 2 dx. Okay, and I'm going to integrate both of those sides. Now the left hand side is fairly straightforward. It's just going to be a natural log. The right hand side I need to split into partial fractions. I'm not going to go through the process of splitting into partial fractions because I've done that in another video, and I'm just going to give you the result of that process. And then what we'll do is we'll look at integrating it. The results I get for the right hand side when I split it into partial fractions is the integral of 1 over x plus 2 take away 2 over 2x plus 1 dx, and the right hand side is just as it is, so 1 over y minus 2 dy. Okay, so now I'm in a position where I can actually integrate these. The left hand side becomes the natural log of y minus 2, and the right hand side becomes the natural log of x plus 2 take away 2 ln 2x plus 1 over 2, so these two cancel out, plus, and I'm going to write this as lnc again because I've got loads of logs. I can write this constant as a natural log. It's still a constant, remember. So let's just tidy this up a little bit. So I've got the natural log of y minus 2 equals the natural log of x plus 2 take away the natural log of 2x plus 1 plus the natural log of c. Now what I'm going to do now is plug in my boundary conditions. So when y equals 4, x equals 1. So this becomes ln 2, this becomes ln 3, take away ln 3 plus ln c. So these cancel each other out, leaving me with ln 2 equals ln c, which means c is equal to 2. So overall I get ln y minus 2 equals the natural log of x plus 2 take away the natural log of 2x plus 1 plus the natural log of 2. And what I'm going to do is combine these logs just to tidy things up. So the left hand side stays as it is, but the right hand side becomes the natural log of x plus 2 over 2x plus 1, okay, because these are being subtracted. And I need to multiply all of this by 2. So it's 2 times all of that. Okay. Now what that means is y minus 2 is equal to 2 times x plus 2 over 2x plus 1, and I can move the 2 over to get y is equal to 2 x plus 2 over 2 x plus 1 add 2, and that's it. Now you could simplify that a bit more if you needed to, or if the question asked for it, but you know, it's fine as it is, so I wouldn't bother. Now this question looks fairly straightforward, and it actually is, but you may be asked to give the final answer in a certain form. So what I'm going to do is I'm going to show you what that might be and how to get there. So first of all, let's separate the variables, and I'm going to get 1 over 1 plus y dy is equal to 1 minus 2x dx, and both those sides get integrated. The left hand side is fairly straightforward. I get the natural log of 1 plus y. And the right hand side I get x minus 2x squared over 2, which is just x squared, plus c. Now at this stage here, what I'd do is I would do e to the power of both sides. And if I do that, I get 1 plus y equals e to the power x minus x squared plus c. Now to simplify this a little bit more, I need to understand a little bit about powers. When you multiply powers of the same number, you add powers. And when you divide powers of the same number, you subtract powers. And what I'm going to focus on is this power that's being added here, this plus c. So what this actually means is this is 1 plus y equals e to the power x minus x squared multiplied by e to the power c. And if I say let this equal a, this gives me 1 plus y equals e to the power x minus x squared multiplied by a. So 1 plus y is equal to a e to the x minus x squared. And finally, y equals a e to the x minus x squared, take away 1. Now this next example looks a bit more complicated than it is. So let's just go ahead and separate the variables and see what we get. We get 1 over y squared dy equals sine squared x over cos squared x dx. Okay, now 1 over y squared I'm just going to write as y to the power minus 2, and sine squared x over cos squared x is tan squared x. Now in order to integrate tan squared x, we need the identity 1 plus tan squared a equals sec squared a. So that's the identity we're going to use. I'm just going to use that to rewrite that right hand side. So let's just plug that in. I get the integral of y to the power minus 2 dy equals the integral of, now if I rearrange this, tan squared a is sec squared a minus 1, so this would be sec squared x minus 1 dx. So now I've got 3 terms which I can actually integrate. The first term becomes y to the power minus 1 over minus 1 equals sec squared x becomes tan x, take away x plus c. So this term over here, that's going to be minus 1 over y equals tan x minus x plus c. And if I flip this over and multiply everything by minus 1, I get y equals minus 1 over tan x minus x plus c, and that's my general solution. In this example, you may be wondering how to separate the variables because you've got e to the power x minus y. Now in order to do that, you need to understand a little bit about indices. Now remember, if you divide powers of the same number, you subtract the powers. Alright, so we can rewrite the right hand side to actually help us. So dy by dx is equal to 2e to the power x over e to the power y. So subtracting powers is what you do here, and that's where this term here comes from. So let's separate the variables now. I get e to the y dy equals 2e to the x dx. So we can integrate that now. I get e to the power y equals 2e to the power x plus c. And if I take logs off both sides, I get y equals the natural log of 2e to the power x plus c, and that there is my general solution. Here's the next example. You're given the boundary conditions so you can find the particular solution, but you do need to do a bit of algebra to begin with before you can actually separate the variables. Anyway, pause the video and give it a go, and I'll go through the answer in a little while. So like I said, we need to do a bit of algebra before we can actually separate the variables. So the left hand side, let's keep that as it is, 1 plus x squared dy by dx. And the right hand side, I actually need to factorize the x out. So I get x brackets 1 minus y squared. So we can separate the variables now. And on the right hand side, I'll get x over 1 plus x squared dx. And on the left hand side, I'll get 1 over 1 minus y squared dy. Now, the right hand side is actually quite straightforward. We just need to use the reverse chain rule. But for the left hand side, we need to split this into partial fractions. I can rewrite this as 1 over 1 plus y multiplied by 1 minus y, and then we can split the fractions up, and then we can actually integrate it. So once you've split up the left hand side using partial fractions, what you end up with is 1/2 times by the integral of 1 over 1 plus y add 1 over 1 take away y dy, and the right hand side just stays as it is, x over 1 plus x squared dx. So I can integrate all of this now. If you're wondering where this half comes from, remember you split this up into 1 over 1 plus y multiplied by 1 minus y, so it's a over 1 plus y plus b over 1 minus y, and a and b both end up being a half, and I can take the half outside of the integral to make the fraction a little bit easier to deal with. So when I integrate, this becomes 1/2 ln 1 plus y take away ln 1 minus y. Now the reason why it's takeaway is because I need to divide by the coefficient of y, equals, now this here would become ln of 1 plus x squared over 2. So I need to divide by 2 because the derivative of 1 plus x squared is 2x, but over here I've only got an x, so I need to divide by 2 to get rid of it. Plus, now my constant I'm going to write as a half ln c. Okay, it's still a constant, but I'm writing as a half ln c because now I can take a half out of all of these terms. So what I end up with is ln of 1 plus y take away ln of 1 minus y equals ln 1 plus x squared plus ln c. So what I can do now is I can substitute my boundary conditions. So y is 2, so I'll just put a little 2 there. X is 0, and if I plug those in, what I end up with is ln 3 take away ln 1. Remember, it's the modulus, so 1 take away 2 is minus 1, but it's the modulus, so ln 1 equals ln 1 plus ln c. Now ln 1 and ln 1, they're both 0, so I get ln 3 is equal to ln c, which means c is equal to 3. Now what I can do is I can plug all of that back into this line over here. So what I get is ln 1 plus y take away ln 1 minus y equals ln 1 plus x squared add ln 3. And I can combine these logs to give me ln 1 plus y over 1 minus y equals ln of 3 times by 1 plus x squared, which means 1 plus y over 1 minus y is equal to 3 plus 3x squared. And what I can do at this stage is I can multiply through by 1 minus y and get all the terms with y on the left hand side and everything else on the right hand side and factorize out the y and then divide by it to give me y equals 4 plus 3x squared over 2 plus 3x squared. So a lot of complicated algebra going on there, and obviously you need to be comfortable using logs. And on to our final example. So if you want to give this a go, pause the video and have a try, otherwise keep watching and I'll go through the solution. So let's start by just splitting the variables or separating the variables as we'd normally do. So if the y's go on the left hand side, I get 1 over y dy equals x sine x dx. Okay, now 1 over y becomes ln y, that bit's easy. But this side here, that's a product, so what I need to do is use the integration by parts method that I've shown you once before. So we need to let u equal x and dv equal sine x, which means du is equal to 1 and v is equal to the integral of sine x, which is minus cos x. So this side here becomes uv, which is x cos x, or x times minus cos x, so minus x cos x, take away the integral of v du, and that will be minus cos x dx. So I get ln y equals minus x cos x. Now this here, this becomes the integral of a positive cos x, which is just sine x, add c. And we can put in our boundary conditions to work out what the constant is. So let's just write down pi over 2 here, and pi over 2 here, pi over 2 here, and 1 here. So what I get is ln 1, which is 0, equals minus pi over 2 cos pi over 2. Now cos pi over 2 is 0, plus sine pi over 2, which is 1, add c. So what I end up with is 0 is equal to 1 plus c, which means c is equal to minus 1. So I can rewrite this line over here as ln y equals minus x cos x plus sine x, take away 1. And I think I'd probably just leave it there, because the only other thing I can do is say y is equal to e to the power all of this, but I think that's a bit more complicated than it is already. So that there is a perfectly acceptable form for the final answer. And that's it as far as differential equations go for Year 2 A-Level Maths. Thank you for watching and listening, and I hope to see you again. Goodbye for now.